The last concept we're going to learn regarding graphs is basically a tool that is nowadays very useful for the analysis and design of machine learning algorithms over graphs. And that's a Weisfeld-Lehmann test of a isomorphism. And for that, let's recall what isomorphism means. So two graphs are isomorphic if they are essentially the same up to renaming of vertices. Okay, which means that there is a bijective function that matches every node of G to some node of G prime, so that two source nodes of a G are neighbors even only if their images are neighbors, and there's the undirected and the directed versions of this concept. You can also define isomorphism based on the adjacency matrices, okay? Because two graphs are isomorphic if they essentially have the same adjacency matrices. It's just that you need to adjust or replace the indices of the node. So what does it mean? It means that you can obtain the adjacency matrix of one from the other by applying a permutation. How does it look like? So G1 and G2 are isomorphic if A1 can be written as A2 when you multiply it from the left by some permutation matrix and from the right by the same permutation matrix transform. And why is it so? So think of it for a while. The goal is to, permute the indices of A1 into A2, so or A2 into A1 in this case. So P adjusts the rows, and multiplying from the right by P transform adjusts the columns, okay, or permutes the columns. That's the idea. Now this is graph isomorphism has an important role in computer science, and theoretical computer science, in particular, complexity theory. It is not known to be solvable in polynomial time. It is conventionally believed to be easier than NP-hard problems. It is definitely in NP. There are some variants that are definitely NP-hard, like testing whether the graph G is isomorphic to some subgraph of another graph G prime. Okay, so that's regarding isomorphism. And why do we care about the isomorphism? Well, for very basic reasons. Suppose that we have a graph G and two nodes V and U over from G. Now, suppose that we want to apply a machine learning algorithm to G, and this machine learning algorithm will give us some prediction about V and about U. Now, suppose also that this algorithm looks at K hops. Okay, it looks only at K hops, and this is quite common, like graph neural networks and so on. And also suppose that V and U have isomorphic induced graphs by their K hops. Okay, so if the K hops of V and U induce isomorphic graphs, and there's an isomorphism mapping V to U, then basically the algorithm cannot distinguish between V and U, and it must say the same thing about V and U, no matter how parameterized, complex, deep the algorithm is. Well, that's obvious, right? The algorithm sees the same thing. It gives us the same answer unless there is some randomization and so on. Okay, this is fine, but still, they are isomorphic. But we'll see that this is true even for weaker notions than isomorphism. These K-hops or the induced graphs do not need to be actually isomorphic. It is enough that they suffice some weaker property, and that's the Weisfeld-Lehmann algorithm, for these algorithms to not be able to distinguish between the nodes. And that's the source of importance of this technique regarding the expressiveness of machine learning models, or models that are learned in machine learning algorithms. Okay, like again, graph neural networks. So this will help us understanding the expressiveness and the limitations of families of functions in machine learning. Okay, so how is the test going? So uh, the idea is to come up with a test such that if two graphs are isomorphic, then you'll the test will say yes, they look isomorphic to me. Uh, so this is like a necessary condition. Okay, if the graphs are isomorphic, then the test will succeed. But the test might also succeed if they are not isomorphic. Okay, so the test is not sufficient. If you say, according to the test, that the graph look isomorphic, it doesn't necessarily mean that they are isomorphic. And the idea is very simple. Suppose that I'm telling you, look, I give you two graphs, G1 and G2. Find a quick proof that these are not the isomorphic graphs. Give me a reason to believe or an actual proof that they are not isomorphic. So you can go and say, okay, let's first look at their node sets. Do they have the same number of nodes? Well, if not, then they are not isomorphic. That's it. Okay? But suppose that they are isomorphic. What would you do then? Then you can say, okay, let's see. Well, the first graph has, say, 5 nodes of degree 10, and the other graph has 6 nodes of degree 10. Then they are not isomorphic. In general, you can group the nodes by their degrees and see whether the corresponding groups have the same sizes. Okay? And if you found some difference, then you can say, okay, fine, they are not isomorphic. But what if that fails as well? Okay, so you can basically further go on with this idea and look at the degrees of the neighbors of nodes and group them according to that. And that's basically what the algorithm is doing, invented by Weisfeld and Lehman. There's an interesting story around the two, and I invite you to go and read about them. And the general idea of this test is what we've seen here. We group colors, or the different way of saying groups is that we color nodes, okay? And nodes of the same color will be considered the same group. Okay, so color, group, I use them interchangeably. Okay, and by coloring, I mean that we assign to them a natural number. We call it kappa, a function kappa that takes as input a node and returns a natural number. That's the color. Okay, now in the literature, it is referred to as WL or 1WL. And that's to distinguish it from the KWL version that looks at K sequences of nodes. We're not going to get into it in this course. Okay, so let's look at the undirected version of Weisfeld-Lehman. The coloring function is based on a hash function. We call it hash, which takes as input a node color C and a bag B of colors. Okay, these will be neighbor colors. Okay, so hash CB is a natural number, is a new color. Okay, and remember, by a bag, we mean that we allow for duplicates. Every element is associated with multiplicity. Okay, the crucial thing about hash is that it is assumed to be injective. If the function hash gets a different input, then produces a different output. In other words, hash CB is the same as hash C prime B prime if and only if C is equal to C prime and B is equal to B prime. If any of these is different, then different color is produced. This is crucial. Okay, now the algorithm will create colorings in iterations, and it will test whether two colorings of the current coloring and the previous coloring are equivalent. What does it mean for two colorings to be equivalent? It means that they define the same groups for every two nodes V and U. The color of V is equal to the color of U if and only if I mean, in according to kappa, if and only if it is true according to kappa prime. Okay, kappa V equals kappa U, if and only if kappa prime V equals kappa U, kappa prime U. Okay, so how does the algorithm look like? Very, very simple. Start by assigning the same color to all nodes. Kappa 0 of V equals 0 for all nodes V. Now, once you constructed kappa I, you define the next coloring, kappa I plus 1. How is it defined? Very simple. Kappa I plus 1 of V is the hash that takes as input the current color of V, kappa I of V, and the bag of colors of the neighbors of V, kappa I U, where U is a neighbor of V. That's all. And you continue, coloring and coloring. When do you stop? You stop when the current coloring, or kappa I plus 1, is the same as the previous coloring, kappa I. Okay? Or equivalency. Not the same, but equivalent. Not necessarily the same colors. And that's it. So we would like to understand, what this algorithm is doing, and does it stop? And if it does stop, after how many steps? Okay, so let's first look at a few examples. So we start with this graph. Okay, and we start by coloring all of the nodes here gray. That's the kappa 0, and then we apply one step. Now you can see here that we color these two nodes orange, same color. Why so? Because they have the same number of neighbors. Okay, this node has degree 3 and this has degree 3 and so on. And the nodes of degree 2 were colored blue. Okay, now we go on to the next step. And now the two oranges suddenly receive new colors or different colors. Okay, and why is it so? Because the orange here has a blue and green neighbor, whereas the orange here has a blue and blue neighbor. So they get different colors. Now, if we continue with a graph where all nodes have the same, have different colors, we'll continue to get a graph where all the nodes have different colors, which is equivalent to what we started with. So basically, the algorithm will stop at this point, realizing that the next coloring will be the same or equivalent to the current coloring. And here is another execution of the algorithm. We color the nodes again according to the degree. But we can see here that once we apply the algorithm again to this graph, it will get an equivalent coloring. In particular, if you look at the two orange nodes, then each orange node has a dark blue neighbor, green, and light blue or sky blue neighbor. And the other orange one has the same bag of colors in the neighbors: dark blue, green, and the sky blue. And so they continue to have the same color, and that applies also to the two sky blues. And this is equivalent to the current coloring, and we're done. Okay, let's look at how we use this algorithm for isomorphism testing. So basically, the idea is the following. You apply the algorithm on both graphs in parallel, and if the algorithm behaves differently at any point of time or at any iteration, then you say, well, they are not isomorphic. Okay? When the algorithm stops to update the when the algorithms terminate, okay, if both algorithms terminate and it didn't fail yet, then you say, okay, it passes the WL test of isomorphism. Okay, so let's look at how the algorithm operates on these two graphs. So they have the same number of nodes. So we say, okay, fine, let's continue to the next step. And then we apply the coloring on the left graph, right graph. And you can see, okay, I produced 4 orange nodes, 2 blue nodes, and 2 green nodes, and same on the for the other algorithm. So it looks okay. We continue. But then on the next step, you see that this algorithm, the left algorithm, produced a color which is the color that you get from an orange node having 2 orange neighbors. But there's nothing like that in the right side. You won't get this purple color there. And so the algorithm behaves differently on the two graphs, and then we say, hey, they are not isomorphic, and they are indeed not isomorphic. Okay, but it's not always the case. Let's look at these two graphs. Definitely not isomorphic, but WL cannot tell. Why is it so? So they have the same number of nodes. So at the beginning, all of the nodes have the same color. But then every node has the same neighborhood. Every gray node has 2 gray neighbors in both graphs. So the next coloring will again color the nodes in the same color, which is equivalent to what we started with. And so the algorithm will behave exactly the same in both of these graphs. So you see an example of graphs that are definitely not isomorphic, but WL cannot tell. And this is an important limitation of WL. Okay, now let's do some analysis or understand how WL is working. So the first theorem here says that basically when we stop the algorithm, it is not like an arbitrary choice to stop it at the first time when things become equivalent. And why is it so? Because if we did continue the algorithm for additional steps, we would always get equivalent colorings. We would always get the same groups. And why is it so? Think of it as follows. Kappa I plus 1 gets as input the colors of kappa I and produces a output. And these outputs are, again, equivalent to kappa I. These are the same groups. Now, kappa I plus 2 will see kappa I plus 1, which is basically the same as kappa I. You just replaced all of the colors, but all of the structures, all of the groups are the same, all of the neighbors, bags, and so on. So it will again produce something similar to what kappa I plus 1 produced up to equivalence. So kappa I plus 2 will still be equivalent to kappa I plus 1 and a kappa I. And so on and so forth. You can continue by induction. Okay? So when we stop the algorithm, we stop it because it's not going to make any changes if you run it indefinitely. Now, the next lemma is very important, and it basically says that what the algorithm does is refinement of groups. It doesn't unite nodes that were in different groups. It can only split groups. And why is it so? Well, what it says is that if two nodes have different colors at some step, then they will continue having different colors in the next step. Okay? So again, the algorithm can only break groups. It cannot recreate groups by joining things that were not together previously. And this is very obvious from the way that this hash function goes, because if you give the hash function two different colors C, then it will produce two new different colors in their output. Okay, because as we said, this algorithm, this hash function is injective, and that's the idea. Okay, so the algorithm can only break groups apart, and so how many steps can it go? Well, how many in every step you break a group and create another group and add, one or more new groups. How many groups can you have? Well, you can only have at most V groups. Okay, so if you create another group every time, or you enlarge the number of groups every time, we'll only reach at most N, or the V number of groups. Okay, so um, that's the idea. The algorithm terminates after at most V steps, and basically the last algorithm says the last theorem says that if we start with isomorphic graphs, then the algorithm will produce the same colors on matching nodes. Okay, so if you have an isomorphism from G to G prime, and it maps V to V prime, then in each step, V and V prime will have the same color. And this is an obvious property, and you can prove it straightforwardly by induction. Okay, and so as we said, if two graphs are isomorphic, WL will say yes. Okay, now some variations of WL for graphs beyond undirected ordinary graphs. So if the graph is directed, we can apply the WL by basically looking at what it is that we see in a node. And now we have the color of the node, and we have the bag of incoming neighbors, and we have the bag of colors of the outgoing neighbors. So we can replace the hash function by this function that takes three inputs. And again, injective and so on. Okay, what if the graph is labeled? So if it is labeled, then instead of starting the coloring in the same way, 0, we initialize the coloring. The first color is actually the label, okay, or some numerical representation of the label. And we continue in this way. And what if we have features? Same idea, and just that we have the initial coloring as a hash of not only the label of the node V, but also the features, okay, XV. For that to be well defined, we need to assume that XV comes from a countable domain. Otherwise, it doesn't make sense to say that such an injective hash prime exists. And that's it. The lemma and theorem continues to hold. So as I said, we are going to see the Weisweiler-Lehmann algorithm, Weisweiler-Lehmann isomorphism test in various cases throughout the course.